Today's topic is the uncertainty principle, and I'm going to explain it in a very concrete and easy to understand way. We're going to apply it to our own lives. Let's start with the basic meaning of the uncertainty principle. This is the formula that represents the uncertainty principle. In this equation, P represents momentum and X represents position. In simple terms, it means that the change in momentum and position cannot be known simultaneously, and it's Planck's constant that defines the limit. See the H and the inequality sign in the equation? That means that the change in momentum cannot be less than the change in position, which is H. In short, there is no way to know more about either value than the number specified by Planck's constant, which is the uncertainty principle. So what is the value of this Planck's constant? The actual value of Planck's constant is about 6 times E34. Notice that the 10th power is 34. How small is this number? You know what we call bilinear, right? These people have dollars to the 10th to the 9th power. If they have $1, let's say that the bilinear in the dular world has $1, and if they have $1, let's say that their bilinear has $1. If their money is again called $1, then 1,000 $1 is exactly 10 to the 32nds of a dollar. The ratio of the height of a person to the length of 100,000 universes is about 10 to 34th. You can get an idea of how small these numbers are. Super Eulara, extremely small. The important thing is that these units are used in the quantum world. So let's put it into real life. For simplicity's sake, let's take a 100-meter race in a straight line. Usain Bolt, a world-class athlete, is known to have a top speed of about 45 km/h. First, we'll find the change in P, or momentum. Since momentum is px/mv, we need to know the mass and velocity, right? The bolt's weight won't change. It's not a variable, it's a coefficient. This means that we only need to consider the change in velocity to know the change in momentum. Usain Bolt weighs 94 kilograms, which surprised me a little bit, but it's 94 kilograms anyway. We know the value of m, so we just need to know the change in velocity. We already have these values, but let's work them out slowly together. First, let's find the change in momentum. As we mentioned earlier, the mass is unchanged, so the change in momentum is proportional to the change in velocity, as shown in this equation. So now we can find the change in velocity. Here's some data from Usain Bolt's actual race, when he broke the world record. Let's look at Usain Bolt's actual velocity change. The actual measurements of Usain Bolt when he set the world record are shown in the table. It's not important, but he definitely has a stronger second half compared to other athletes. You can see that his speed barely decreases after 80 meters, which is a bit different from other athletes who start to pick up speed at 60 meters. Anyway, let's get back to the point. Now we need to find the average speed and the change in speed for each section. For the average speed, we just need to divide the distance by the time, so I've done that for you. We can divide the speed by the time. Here, I've divided the distance into bins of meters to 20 meters and 20 meters to 40 meters. It's not perfect, but it's a good enough approximation. After all, we're dealing with huge numbers. Now we need to find the change in velocity. Based on the section with the largest velocity change, the velocity change is the difference between the first and second sections. The first section is meaningless, so we'll leave it out. The difference in speed is 451 ms. It would be more accurate to use the vector value of velocity, but since it's a straight line, it's probably the speed. And I used the largest value to make it as strict as possible. We need to scale back the exaggeration to make it resonate. We can't just use the velocity difference, it's a change, so we need to divide it by time again. So let's divide 4.51 meters per second by the time difference between this section, which is 175, which is about 256. Now we can find the change in momentum. The change in momentum can be represented by the change in velocity and the change in weight. We can calculate. Delta P is m delta, which is 94 times 256, which is 242.25. It's not a very precise calculation, but it won't stop us from our conclusion, so let's take the next step, using the number 256. Okay, so now we can see how far we can tell Usain Bolt's change in position. If we tweak the equation just a little bit, we can tweak it so that the change in distance is inversely proportional to the change in momentum. If we substitute the above values into this, we get the minimum value of the position change that we can see. Let's substitute the values above. The resulting value is a very small number. This is the smallest length we can perceive in the real world. More precisely, it's the smallest range of displacements per second that we can observe. This is why I said earlier that it doesn't matter if you approximate it. It's got a minus 34 after it, and it doesn't matter if the number before it is 0.1 or 10. How small is this? The mm is only minus 3 power of 10, the nano is only minus 9 power of 10, and the pico is only minus 12 power of 10. As you can see from the result above, that's minus 34 power. An atom is only about 10 minus 10 power meters in size. A light year is 9.461 plus 15 meters, and the diameter of the universe is 46.9 billion light years, which is 444,1318 meters. This means that what the above values represent is more than 100,000 times smaller than the atoms in the universe, if the universe were only atoms. We can observe Usain Bolt moving 100,000 times faster than an atom in a universe the size of an atom in a second with greater precision. That's the principle of indeterminacy, that even if there's a person in real life who is thousands of trillions of times faster than the speed of light, we can still know the exact motion of that person. That's why we can't experience the principle of indeterminacy in our everyday life. But in the quantum world, it's a different story. Because it's such a small world, we can't measure the change in position and the change in momentum. That's why the quantum world is such a small world. What happens when Planck's constant gets bigger? I've had a lot of questions and misunderstandings about my previous video, so I thought I'd explain. The idea of imagining a situation where the Planck constant gets bigger was to help people understand what happens in the quantum world by applying it to everyday life. My videos on quantum mechanics will continue to get more interesting and deeper. Next time, we'll talk about the behavior of a bolt when Planck's constant is large, which means that what happens in the quantum world becomes real.
Knowledge is power.